Alright, another coronavirus stay-at-home lockdown type of project. This one's been sitting around for at least 3 years since I acquired it at one of the vintage computer festivals Midwest in the Chicago area for a few bucks. It's a Heathkit IP-27 regulated low voltage power supply. And I have plenty of power supplies, and the reason I bought this one was when I was a teenager attending high school in Germany in the 70s, our electronics lab, which was newly formed at the high school, realized they didn't have any test equipment for the lab. They just had the lab. And what they did is they invested in Heathkit test equipment for all the lab stations. And the students who had registered early, in other words the previous year, for the new lab starting the subsequent year, were given a chance to come in and work on building all the kits. And it was quite a jump because, of course, nobody then going into those classes had any knowledge of electronics, so they were trusting the students to do a decent job, of course with supervision from the teacher. And we spent a good part of the summer, probably, I don't know, about 7 or 8 kids, building a bunch of oscilloscopes and power supplies, meters, all sorts of things, function generators. And I am pretty sure that the IP-27 was the first thing that I built. I don't have any photos going back then. The period is about correct, this style. There were some other power supply models we built as well, but they all had this style. And this one looked so familiar to me. I thought, I know I've never seen or used one of these in my career. The only time I would have worked on one of these things is if I built one back then in high school in Germany. So I grabbed it and just did a very perfunctory power up and made sure that I got some activity on the meter when I turned the knobs. But beyond that, I don't know if this works or not really. It's quite crappy and dirty. I think it's going to require a lot of restoration. It's obviously been well used. There are largely illegible tags from the 70s. Looks like 71 and 72 on there. On the side, it says this was the property of D&B Auto Radio, and at some other point it was the property of A.B. Dick, which of course is one of the companies that makes small offset printers and other things for print shops to use. And so it went through different owners. I would suspect that A.B. Dick wouldn't have bought this from DB Auto Radio. I'm guessing it went the other way, so maybe it was in the A.B. Dick laboratory or factory and then got sold and the auto radio place had it. I don't really know the history. The Heathkit label is quite the mess, but it is there, sort of. Serial number looks like 09315 maybe. There was a calibration sticker over this that was then poked through. And power supply calibrated, not verified. Use a calibrated multimeter to check output. So my goal is to see if I can restore this as fully as possible. And like I said, that's going to mean taking the case apart, removing the front panel at least, trying to give it a bath and get as much crud off of it as possible. and then go to work on the circuit, replace parts that are bad, do whatever I can within reason to make it working. I'm concerned about all this tape around the meter. I have a suspicion that once I remove that, the meter's going to fall apart. But at least it's not badly cracked that I can see, and the plastic looks pretty clear. It had a label over it. That makes me suspicious of the meter maybe not being fully operational, that somebody would put a sticker over it. And notation to use a multimeter to check the output also doesn't speak well for this meter. But you never know until you get into it. If I can find a suitable meter of similar size and capability, I might replace this if it turns out where it doesn't work. So just a little about this IP-27 power supply, bit of the history. According to Chuck Penson's complete book of Heathkit test equipment products, an invaluable resource. Now for this one I haven't checked Jack Tranter's also excellent book. It's not quite as complete as Chuck Penson's, so I've just gone to this one first. And here it is. The IP-27 says it was sold from 1967 to 1975, and at the cost, presumably in 1967, of about $77. According to a couple of inflation calendars I've looked at, this power supply was roughly $600 in today's money. I'm not sure if that's a really complete picture of this, because that tends to be factored in with buying power and some other variables which may not be applicable here, but let's just say it wasn't a cheap power supply. And it was an upgrade of the IP-20, which had a regulator tube, and it replaced that part of the circuit with a solid state equivalent, and they restyled the cabinet and slightly increased the price, and they said it was finally replaced with the IP-2700 series, which you probably have seen these if you are into old Heathkit things. They all had the same factor. There were quite a few different models giving you different voltage and current ranges, and the choice of a analog meter or a digital meter. And eventually this power supply was more or less replaced by the IP-2718, which is a real classic. They made tons of these things over a fair amount of time, about 14 years. And I have personal experience with these as well. And it's a good power supply. Anyway, so it says that this started in 1967. And I happen to have two different Heathkit 1967 catalogs, the Winter 1967 and the General 1967 catalog. The Winter catalog has a fairly abbreviated test equipment section, and all this being a smaller, presumably less critical catalog, it doesn't have color photos for the most part, if at all. And the power supplies, here's the IP-20, which look like this. So as Chuck Penson's book said, that feature-wise, specification-wise, and everything, this and the IP-27 are essentially the same meter, same specifications. Obviously a very different form factor, but it has the same knobs. You know, there's your standby power switch, your range switches and potentiometers, and so on. A couple of indicator lights, I think, to show you what the meter's showing. Obviously a smaller meter, but The IP-27 does not appear in this catalog. Here in the full catalog for 1967, it has a better picture of the IP-20. Shows the internal circuit. You can see that it does have some transistors in it, but also apparently has one vacuum tube somewhere. Anyway, also conspicuous by its absence is the IP-27, which, you know, should have shown up in here, but that was all the power supplies there right here, and it's not there. Now my Heathkit catalog collection jumps to 1970, and this is their full line 1970 catalog, so, you know, a couple years later, and here it is. The IP-27, $91. The online inflation calculators I consulted also translated $91 in 1970 money to roughly $600 today, but again, I don't think that's a true representation of what these kits would have cost by today's incomes and standards of living and real inflation. Those numbers can be misleading. Anyway, still, it seemed like it's a bit of a premium priced piece of kit, and they had their somewhat simpler power supply there. It doesn't have the coarse and fine adjustments. Similar in many ways, just not as nice, and considerably less expensive. And I actually had one of these, but a later model with a different styling and paint scheme, but same circuit. I think it's the first Heathkit that I actually bought with my own money right after I moved from Germany to the States. I had to leave all my test equipment behind because it weighed too much, so I started acquiring new Heathkits around that time. And already by 1977 they were into the different color scheme for this product, under of course a different model number. Heathkit was famous for that. They would reissue the same designs over and over and just restyle them and maybe make a couple of tweaks, but often not, and sort of perpetuate the design for quite a long time. They would change the model numbers when they did that, of course. So enough of the history on this. There's the top cover off. There's actually a live spider in here. That's just kind of amazing. And he ran into the transformer. I'll get him later. The original rubber feet came off. Those would be the 3M bump-ons. Two of them did come with this, but they were taped on, and they're pretty much trash. The rubber's really hardened, and while this color is still available, you have to buy a ton of it to get just a few, whereas the black bump-ons of the same design are still quite commonly available. So I'm going to have to replace these with the black ones, which I have some in stock. And there's with the bottom cover off. It looks very clean inside. No signs of smoke anywhere, although this cap looks like it may have seen better days. I think I'll probably replace most of the small caps. I don't know about those big can capacitors. I'm reluctant to change those if I don't have to. The handles have been released and they're filthy. The covers that covered them up have come off. There are supposed to be 4 of these, but one of them was missing, along with the screw that goes into one of these threaded spacers. So I'm going to have to fabricate one of these. It looks like it's 16 gauge and from the weight aluminum, so I can get that at the hardware store if I don't already have some, and make a new one of these. And it's just matte black, so that shouldn't be too hard to fabricate. Now to see about getting the front panel off, because that's the one that needs cleaning the most desperately. And it may just be a cosmetic cover over the sheet metal internal one. I'm hoping so. Okay, so the knobs have come off, and now I got to take out, looks like 4 nuts, 2 screws here, probably take the meter off, and may have to undo these too. It looks like it. The old power cord is just about rock hard and cracked, so I have to replace it. I'd like to replace it with another flat one to keep the same look, but if that doesn't work, I'm going to use one of my stock of round power cords. And I think I have some cable grips, strain reliefs of about the same size that I could put in here. Otherwise I can put in a regular grommet and put a electrician's knot on the inside or something like that. I want to get this meter off the panel so I can clean it. And these nuts here are being really hard to get at and hard to budge. They're really tight. I can't get them with my regular nut drivers or wrenches due to the thinness, so I think I'm going to have to fabricate something at least for the inner nut to hold it in place. I don't know if these can actually be cranked around, if the actual bolt's turning or what, but I'm going to make something out of sheet metal here. I've got some 16th inch aluminum here. I'm going to make a couple of narrow wrenches, 3/8 of an inch opening size. This is probably going to give me enough metal to make one of those handle brackets too. Just using my combination bending brake sheet metal shears and sheet metal roller to cut this to size. Okay, 2 pieces, 4 inches long, 1 inch wide. I'm going to cut the sides down to make them a little more manageable, make them a little narrower. And then at the end I'm going to form the wrench head with a 3/8 inch opening on it. So there are the 2 wrenches roughed out on my bandsaw. And now I want to focus on getting these honed to exactly the right width to engage the nuts. And there's one of my homemade wrenches on the inner nut. And then the other one on the outer nut. And this is going to be a 2-hander. Okay, that worked great on that one. I think the one on the right's maybe a little tighter. Okay, that made quick work out of it. These were well worth the 10 minutes or so it took me to make the 2 of them. Okay, the meter's out and everything attached to the front panel is off. The neon bulbs just pull out of their filter holders, which I may take off or I may not. Okay, the bezel and the front panel are off, and I'm going to break these lenses if I try to take them off, so they're going to stay on through the cleaning process. Meanwhile, the chassis is here, and everything's just sort of being held in place by the soldered connections at this point. But there's not a lot of weight on that, so it should be okay. So the first line of attack here is a good long soak in pretty warm soapy water. I've got the top and bottom panels, the bezel and the control panel in there, although they're a little bit hard to see. And then the knobs and the handle brackets, all 3 of them that I have, are sitting in a smaller container, primarily so they don't get lost. And I just added the 2 rubber handles, not the steel cores, but just the outer parts, which were the dirty parts. Okay, I snapped the cover off the meter. I wish I knew what the specs on this were. I don't have the schematic yet. I did order a original Heathkit manual for this power supply, but I don't have it yet. It seems unlikely the meter would be bad. It seems more likely that whatever circuit that drives the meter had a fault in it. It seems unlikely it would get burned out, and it doesn't look like it suffered any physical damage. So I'm going to get busy on this with the goo gone and see if I can't get a lot of that adhesive gunk off of there. Okay, I've got the cover for the meter soaking in my Tech Spray label and adhesive remover, and I've got, just fresh out of the bag, one of my plain toothbrushes, or plaintoothbrush.com plain toothbrushes, which are good for technical work. Nobody sells these in drugstores because they're not trendy looking, but they're exactly what you want for technical work. So I'll be doing some scrubbing on this and probably using the same brush to clean off the knobs and things like that in a little bit. Okay, well, it's not perfect. It has a couple little scratches and some marred areas that, short of sanding it or something, I'm not going to correct, but it's much improved. Certainly doesn't have any adhesive residue left on it or any of that gunk. Alright, the knobs are drying off. The top and bottom panels, the front panel and the bezel are drying off. The discoloration is due to areas that are still wet. Obviously the top panel had a lot more grunge and wear and ground in dirt. It took a lot more working it over with a nylon bristle brush, and where that didn't work, a brass bristle brush. That takes off quite a lot of paint, so I'm kind of interested to see how it ends up looking on here once the all the water's evaporated and I can see the true color and pattern. I'm not sure if I would leave it mottled, if it does look mottled, or if I would try to go and get some sort of a matching paint and give it a shot on top just to make it look better. Don't know yet. So I have a little bit of adhesive remover on the bottom panel where the feet were, trying to get that cleaned up a little bit. And while that's soaking in, I'm going to make one of these brackets. And because the 16 gauge aluminum is too thick to use with my sheet metal bending pliers, I'm using my bending brake here. And I've got a nice piece. I didn't do the calculation to see how much length I was going to lose on the corner, so I made it oversized, and I'm going to mark it next to a real one to see how much I have to cut off. So they're cut down to just outside the lines now. I have to do a little sanding. I think I'm going to use my bigger belt sander for this. Alright, the part is made, and I've got some satin enamel black, which I think will be the closest finish I'm going to get. So we'll do that now. Hopefully I don't have too much dirt on that. I wiped it off really well with alcohol and a lint-free wipe, and it already looks like there's dust on it. Well, it is a wood shop, and I don't have a filter fan here, so well, hopefully it'll be alright. So this is the top, and even though it looks mottled, it's not completely dry yet. I gave it a wipe down with alcohol, and it has a lot of little cracks and texture to it here. It's a very satiny textured finish after working it over. It was kind of a wrinkle finish originally, and I've knocked a lot of that off with my cleaning operation. So I'm going to let it dry overnight, and in the morning I'm going to go down to the hardware store and see if I can find any kind of a spray paint that's close enough to this, and you know, if I can get a reasonable beige or sand or whatever khaki color this is, I may get it and just give it a shot of that. And if not, I'll leave it the way it is, and that'll just have to be it. It's better than it was. Alright, which one is the new one? Figuring that the inside paint on the panels was the closest to the original color, or even here, but probably this. I found this Rust-Oleum product. It's a camouflage paint, non-reflective. I don't know, it's sort of a tan color, but it doesn't say on here. Here it is, camouflage sand. And you know, it's pretty close. I'm going to do a test spray right in this area, and after it dries, see how closely it matches. If it's reasonably close, I'm going to shoot the top and bottom panels with it. I'm going to attack these marks that have been made on here with isopropyl alcohol first, and if that doesn't work, I'm going to try the Dissolve It product that I've had good luck with in the past. Well, the alcohol did take a lot of it off, but not all of it, and the Dissolve It did nothing. I'm assuming these are from Sharpie markers, and acetone will usually do a better job than will alcohol, but I'm leery about using it on this paint, so I'm going to try a little bit around the corner and see if any comes off on the Q-tip. Well, the acetone did work the best, although it did slightly discolor the paint where I used it. I used it on Q-tips very sparingly with minimal pressure, and I think it's, even with the slight blotchiness, there's blotchiness on the panel already from other, you know, cosmetic imperfections it had due to wear and tear, so I don't think they're going to stand out all that much. I'm going to give this thing a good rub down now with isopropyl alcohol, try to even things out a little bit. So that's about as good as it's going to get, I think. The rear panel has the fewest blemishes on it, but it does have just a lot of dirt and residue of the Heathkit label and a calibration label. I don't want to take this apart because then everything will fall apart, and it's sort of what's holding the case together, so I'm going to just kind of clean this in place. Well, it's much improved. There's a white blotch where the label had been, and some slight discoloration here and there, a couple of paint chips, but definitely much better looking than it was. Okay, well, this isn't great. It's not really the same color. It would be okay, I think, if nothing else has a contrasting color. But there was another can of camouflage spray paint at the hardware store that was a somewhat darker, slightly browner version, and this paint is only a couple of bucks a can, so I think I may go back on my next trip and get that can and see if it's any improvement, and then decide which one to use. But I think I'm definitely going to repaint this. It will look better in the long run, I think. Here's the other paint. This one is called Khaki. Already I'm liking this one. We'll see how it looks when it's dried, but to my eyes, when wet, it's a closer match for the original paint. Okay, that stripe across the middle there is the new khaki colored paint, and to my eyes it matches much better to the original than the sand colored paint, although that would have been viable too. So I think I'm going to give these a shot with the khaki. 3 light coats. Okay, I want to test this meter and see if it still works and verify it for reasonable accuracy. To get such a low current. It's a 100 microamp meter. I've rigged this assembly up on my workbench, and I've got a digital multimeter in milliamp mode wired into it in place of the meter right at the moment, but the circuit I have here uses an op-amp, and to drive the input I have a 10K potentiometer wired between circuit ground and the positive power supply, so I get a 0 to 10 volt span because my power supply is plus and minus 10 volts. I could have rigged this up to work on a non-bipolar supply, but I just thought it would be just as easy to do it with a bipolar. I'm using a 1458 dual op amp, which is basically two 741 type op amps with a somewhat higher specification, but basically a 741, or two of them in an 8-pin package. And I have to change my battery on the camera. Okay, back to this circuit. It's just a non-inverting op amp amplifier arrangement. I don't actually have this 10K resistor in here. I'm going directly from the wiper of the 10K pot into the plus input. And so that's going to swing from 0 to positive 10 volts. And then I have this resistor that goes from the output back to the negative input. It's comprised of a 100 ohm resistor on my breadboard plus the meter in series. The meter is going to have a pretty low DC resistance. I don't know exactly what it is, and I didn't measure it. I just assumed it would be not that many ohms. So then I have a 68K resistor. It's actually just a resistor on my resistance box. It's not a decade box, it's just a variable resistance box. Instead of doing the calculation, I just did it empirically until I got a swing of approximately 0 to 100 microamps in the feedback loop here. And so I want to turn my power supply back on and re-verify that I've got that. So I'm going to go here and turn my power supplies on. I'm reading 0.1 milliamps, which is 100 microamps. It's a little over, it's really 0.1161, but that's fine for what I'm doing here. And as I adjust the pot here, let's see if I can do it with one hand. There we go. Goes down to basically 0. And then as I turn the pot back to its other extreme, I've got roughly 100 microamps. So now I'm going to introduce the meter into that circuit. I did it this way first to make sure that the circuit wasn't going to be generating way too many milliamps and damage the meter. I don't know if it has any protection in it or not. But now that I know that I'm in the ballpark with my circuit, I'm going to hook up the meter and keep this one in series. The circuit should compensate somewhat for the variable resistances. Okay, I've just turned my power supplies back on, and I'm getting a reading on the meter here. It's saying that I have 100 microamps going through it right now, since that meter's in series with this one, which worries me because it should be full scale here. Well, that's interesting. Maybe it's not really 100 microamps. Maybe I got the wrong information. So I'm going to select down to 47K here, which will give me more current, and more current again, and more current. Whoa. There's a big jump. So there's 1 milliamp going through this according to this meter, and that's giving me a full scale reading. As I crank my pot down, I'm not getting it to go below this level here, even though it says I've got essentially nothing in the feedback loop, which worries me a little bit. Well, it's certainly capable of swinging the full scale. See if I can set my camera up so I can still see the meter. Okay, I've got nothing happening there. Even though the other meter says there's quite a swing in current. Now I'm getting nothing on that meter. It's not reacting at all. What if I short out the meter movement? Okay, so the meter movement is shorted out, and I still have this reading here, which is not good. Let me try adjusting it. Maybe the zero is just... Okay, it was like it was stuck. And when I moved it around a little bit, it jumped down. So let's see if it's responding now. It goes up to that point and it acts like it's hitting something. It moves great, and then it just like, it bangs out there. Then I've turned it down. Yep, it's got a stuck movement. That is its problem. Okay, now it's moving. It's going from 0 milliamps to it's actually a 1 milliamp meter, the way it's responding here. 1 milliamp down to 0. Seems working good now. It's just that it seems to be off by an order of magnitude from what I thought the schematic said it should be. But it seems to be working now. I don't know if I bang on it and do stuff, if that's going to affect it. I don't know, it seems to be working now. No problem. Okay. So, hopefully I won't have to replace this. I thought I might have to try to find another meter movement that I could stick in here. But right now it looks it's okay, as long as it's not somehow got to be a different value than it should have been, and I very much doubt that it is. It's I don't know how damage could cause the movement to jump by an even order of magnitude. Okay, what's going on in this little circuit that I'm using to test the meter for this power supply? The circuit is one that I used early in my career, probably around 1978. I had a product I was helping to design that had to swing a D'Arsonval meter movement based on a small high impedance analog signal, and obviously I couldn't just drive the meter directly with that, so we also needed to be able to scale it. And this was something I came up with and was pretty pleased with myself at the time, but it's nothing revolutionary. It's probably pretty common for all I know, although I honestly haven't seen it elsewhere. So I've got an op amp. It's a 741 type op amp. Nothing special about it. Plain vanilla generic op amp. I've got a voltage source, which in this case is just used to swing the meter, so it doesn't have to be anything in particular, but I'm using a plus and minus power supply on this op amp. I could have rigged the circuit up to work on only a plus 10 volt supply, but it would be slightly simpler if I did it with a plus and minus supply, but nothing here is swinging below 0 volts, so the minus supply is sort of superfluous here. The 10K potentiometer I just grabbed out of my junk box is a good impedance for this voltage. It doesn't stress out the potentiometer at all. There's not that much current flowing in it. But swinging this pot from one end to the other, I can get potentially between 0 and 10 volts. I'm just going to turn it as far as I need to get the meter to swing to its full scale. Initially, I did not know what the resistance of the meter was in a circuit. It can sometimes read a little differently if you're just reading it statically than if you're actually putting it in a circuit. So I wasn't sure what it would be, but I figured it would be, you know, probably somewhere between 10 and 100 ohms, something like that. I want to have a minimum resistance in this part of the circuit, so I just threw 100 ohms at it. The configuration is a non-inverting amplifier, a classic op-amp circuit. Many cases I could put a series resistor here. You'll see that a lot. It's not needed here. Number one, the input impedance is very high, so I can just put a signal into it directly. But also, this is a voltage divider here, and so there's already resistance between any actual signal like 10 volts and the input, so it's immaterial. A resistor here is not needed. It also doesn't factor into the calculations for gain. Now, the configuration for a non-inverting amplifier is to take the output and run it through a resistance back to the negative input. That's your feedback, negative feedback. And then there has to be a resistor from the negative input to ground. And it's the ratio between this resistor, the feedback resistor, and this resistor to ground that controls the gain of the circuit. In other words, how much more will the output voltage be than the input voltage. Now, I don't want a lot of gain here because I've already got 7.4 volts or something. That's empirical. Let's say it would go up to 10 volts. The op-amp can't swing completely to its supply rails, so I don't want the output to go even to 10 volts, but I can control that by adjusting the potentiometer so it doesn't max out the op-amp. But the output voltage is not the point in this circuit. I'm not using the output voltage for anything. It's just to get this feedback loop working, and the meter itself is in the feedback loop. So I took a reading here of 7.44 volts from the positive input to ground when the meter is reading full scale. And I learned from the Heathkit schematic that it is a 1 milliamp meter instead of a 0.1 milliamp meter as I originally thought. It's not, doesn't say that on the meter anywhere, but that's what the schematic and the parts list says. So in order to get it to read full scale, I need to put 1 milliamp through this feedback loop. Now there's a couple characteristics of op amps, is that essentially no current flows in or out of the inputs. So you can treat them like an infinite impedance. It's not really infinite, but it's really close. It's an extremely large impedance, so essentially no current flows in and out. Secondly, the op-amp will try, if it has feedback, negative feedback, it will try to adjust things such that both inputs have the same voltage. So since I know that 7.44 volts on the non-inverting input gives me a full scale on the meter, I know that at that point I'm going to have 7.44 volts on the inverting or negative input. I empirically found out that a 6.8K resistor on my resistance box gave me the right range for this. But when I actually measured it, the tolerances are quite low, and it was actually a 7.4K resistor. So I put that here in the circuit. Now going back to what I said just a moment ago, if there's no current flowing in and out of this input, then the current that comes from the output and goes through the meter can't be going into this, nor can any current be coming out of it. That means that current has to have somewhere to go, and it's going to come out of here, out of the output. It's going to go through the meter, and then it must return to ground. So since I know I've got 1 milliamp here maximum at full scale on the meter, that means 1 milliamp is doing this. And I can adjust it from 0 milliamps here to 1 milliamp by using the potentiometer. So the calculation for a non-inverting amplifier of the op-amp type is the voltage input, in this case 7.44 volts full scale, times 1 plus the ratio of the resistors. Now originally I just said, well, I'm going to assume that this is 0 ohms, but that was kind of silly. So I threw an initial number at it, and it didn't really matter since I was going to adjust this value empirically until I got 1 milliamp here. So after doing that, I went back and measured while the meter was at full scale, so I knew it had 1 milliamp going through it. I used a high impedance voltmeter to go across the meter and measured 0.05 volts. Applying Ohm's law to that, 0.05 volts divided by 1 milliamp gives me a 50 ohm resistance or impedance in this meter movement. I measured this resistor and it was 99.1 ohms. It's a fairly good precision part, so it's really close to the rated 100 ohms. So let's just say it's 100 ohms, and this is 50 ohms. So this feedback resistor is 150 ohms. So I put that here in the equation. I have the measured 7.4K resistor in my resistor box, so I put that here, doing the math, and with a V in of 7.44 volts, applying that to the equation gives me an output of 7.59 volts at full scale. So I marked 7.59 volts here. Now let's work it back as a sanity check. I know that at full scale this input has to be the same voltage as this one, so 7.44 volts. I subtract that. This is essentially a voltage divider, so the voltage at the middle is going to be the voltage from here to here, 7.44 volts, and so I can just subtract that from the voltage here, and I get 0.15 volts, which makes sense because if I've got 0.05 volts across the meter, and that's 50 ohms, then I should have twice that across a 100 ohm resistor. So that gives me 0.1 volts. 0.1 volts plus 0.05 volts equals 0.015 volts. And once again, that adds up, because if we add that to the 7.44 volts, we get the 7.59 volts here. So all the math works out. It matches the actual measurements taken in the circuit. And the upshot is that by swinging this input voltage with my potentiometer through a 0 to 7.44 volt range, I get a 0 to 1 milliamp current passing through my meter, and thereby going from 0 to full scale on its range. Simple enough. Well, I've got the Heathkit label stuck back on there. It was really a chore to get it unwrinkled. I just burnished it from the back, and even then it's still got some ripples in it. I could not get it to lay down completely flat, but at least it's on there and it looks a lot better than it did before. And I've put on a new power cord. The old one was one of the compression types that gets squeezed over the cable, and that would require a flat cable. I'm just using a regular round cable, so I just put in a different grommet and put a couple large wire ties pulled tight on the inside to keep it from pulling out. I'm not too worried about it going in. Okay, it's time for the deoxit on all the switches, the couple of slide switches and the couple of rotary switches. The four most critical transistors in here are the two pass transistors on the back. They're both identical. And then these two, I think they're all germanium PNP transistors. These two are the same kind, and these two are the same kind. There's also this one here, but from what I've read, it rarely fails. These two are notorious for failing if a certain modification hasn't been made, which I plan to make because it hasn't been made before. If you change the range switch rapidly, it can cause these transistors to wink out here. Easily damaged in that way unless the mod is made. I don't know if these are good or not, but once I get on a roll with this, I don't want to be held up by finding the transistors are dead. So I decided to go on eBay, and I found a seller that had about 4 of these brand new, and I ordered 2. And then I found a guy who had about 5 of these, and I ordered 2. So those should be coming in a couple of days, and if I need them, I've got them. I've got all the capacitors I ordered to go in here, and the only 2 I have not planned to replace are these 2. They appear to be in excellent condition. I'm just going to see what happens running it with the old caps. If it acts flaky or acts like there's anything wrong with these, if they get warm or anything like that, then I'm going to look into replacing these. It's probably not going to be possible if I have to replace them to get ones that are identical, or if I do, they'll be old and no good either. But there's nothing all that remarkable about these. This is a 100 microfarad 250 volt, and this guy is, I don't know what it is. The marking is under the band, but it's not all that remarkable of a value by today's standards. And it's generally acceptable to replace these with clusters of smaller electrolytics wired in series. You know, I don't know if I can easily find a 250 volt electrolytic and 100 microfarad in a different form factor, but I can probably find some. They may be smaller microfarad values, different capacitance values. This is also, I think, a multi-cap, so it's got 100 microfarad at 250, a 40 at 250, and a 40 at 200, all inside the can, and this one may be similar. But once again, these can be built up out of smaller capacitors if need be. Okay, for reassembly, I'm starting off by putting the binding post back on, and then the meter movements back on. Everything else mounts from the back. Well, it was quite the chore to get all this stuff on the front panel back on. There's a strain or a terminal board which goes onto one of the meter mounting screws, and that was a real pain to do. I had a hard time getting the nut down in there. I actually ended up using a McDonald's or equivalent fast food straw that was just about the right diameter to jam the nut in there, and then tacked it with a little super glue and accelerant and used it as a long reach nut driver, and then just tore it off once it was on there. That worked. And I managed to break one of the neon bulbs, so I'm going to have to go online and buy a replacement for that. But at least that part of it's done. And now I have to put the bezel on and mount the front panel. Well, putting these knobs back on, I found out that the switch ones were in pretty good alignment. The pots were adjusted so at full counterclockwise they were at 9 o'clock, which meant they were going way too far clockwise, covering up the word fine when they were full clockwise. So I pulled out the inserts, the zinc inserts, and realigned them. This one went in okay. This one started to produce cracks in the shell, which happens to these, especially when they're a bit older. When you push those in there, the plastic is not as pliant as it used to be. So I stopped it before it went too bad and wicked some CA glue into the joints, hit it with accelerant from the inside, and then I took the strip sander to the zinc insert and just took it down so it fit in more easily. And once it was in there, then I hit it with, I filled the any gap there was with more CA glue and accelerated it again. And I think that's going to work out pretty well. Now I have to fit these guys because now they're sitting up too high. I found out that whoever assembled this originally put these inserts in backwards. They're tapered, and it's supposed to be small end first into the knob, and they've got it the other way around. So I need to pull these out, realign them, and put them back in, and hopefully the knobs don't split. Alright, well, I've got the power cord secured through a whatever these things are, combination strain relief and cable clamp to one of the screws for this capacitor, and then its leads are terminated to this terminal strip where the old power cord was. So that's taken care of. And I almost pulled this whole thing off the bench to its potential ruin because the power cord got wrapped around my foot as I was sitting at the bench, and when I stood up I nearly pulled the whole thing off the table. That would have been nice. So the next thing to do is replace this capacitor and these three capacitors with the new ones that I bought here. And then to make the modification to this terminal strip in the process with this Zener diode and this capacitor per the modification instructions. Okay, all the electrolytics are in there, and this one over here. And for this value I had to put two in parallel of 3/5 and 2/5 the total value to get slightly more than the rated value. This one here, I thought I'd ordered one in an axial, but it turned out I ordered it in a radial. That's alright, it fits. I have to put an extension wire on it here, which is fine. The original part wasn't insulated in either of these. There's nothing else for them to short out to. The only place where there is some insulation is on this capacitor here, which has to bypass the relay, and that had a piece of insulation tubing on it, which I just reused here. So all the smaller capacitors have been changed out now. Alright. I get a hum. The fuse didn't blow. I'm on the 0.5 to 5 volt range. I'm metering voltage. And nothing comes up. Maybe I need to... There we go. Huh, okay. 5 to 10 volt range. Starting at about 5. Going up to about 10. 10 to 15, it's up to 10, and I can go to 15 approximately, 15 to 20 on the red scale there, 20 to 25, 25 to 30 approximately, 30 to 35, 35 to 40, 40 to 50, and oh, that was 40 to 45. This is 45 to 50. There should be the voltage neon here, but that's the one that's broken. So I've got it turned down. I'm going to turn the DC off. I'm going to slowly change my range, even though I have the protection in there now. I don't want to risk it by just whipping it around. 10 to 15 sounds good. Alright. So the power supply is basically functioning, although it has no load on it whatsoever. Next thing I want to do is hook up a bit of a load to it. Make it do a little something. And then I'll go through the whole calibration and setup procedure in the manual. I just want to prove that it can put some juice out. Alright, I've hooked up my electronic load. I've set it to current mode, I think. I haven't used this recently. Hope I'm doing it right. I've set it for 10 milliamps of load and hooked it up to the power supply. So, let's see. I need to... It is on already. I need to turn it on. The load is currently turned off. So I got it set to 10 volts. And I'm going to... where's the set button on here? Okay. So I've set the current to 10 milliamps. I'm going to turn the load on. I've got that lamp when I switch the meter over. Okay, the supply is measuring 9.24 volts and 10 milliamps, but it's not actually supplying amps. I don't think I've actually turned the load on yet. Okay, now the load is on. Now I'm getting some amps. And the meter has come up. It's still on 50 milliamps, so I should be in a good range. There's some adjustability there, not very much. Not sure if that's working correctly or not. Let's make it do a little bit more. I want to go to amps again and make it go up to, I'm doing this the hard way, to 100 milliamps, and I set it. Then I go back to the normal display and it doesn't appear that it's actually trying to pull that current out of it. Oops, no voltage. Yep. So I'm back to my voltage here, and the power supply is still on. I verify that the load is getting almost 10 volts, but if I'm watching the voltage and I engage the load, it's going way down, clunk. So, and I heard the relay clicking, so it apparently thought I was trying to limit it. I think this is actually the maximum current, maximum of 50 milliamps, and I've got the knob fully counterclockwise, so I'm going to crank that all the way up, so it should be able to deliver. But I'm in 50 milliamp mode. That's kind of dumb of me, isn't it? I should go to the 150 milliamp mode, and I've got it maxed out. So let's see what happens now when I engage the load. Okay, it dropped ever so slightly. Now what am I getting if I measure current? It says I'm measuring current. This is on the black scale, so it's pulling roughly, well, 10 on here, so roughly 100 milliamps. And so it is putting out, putting out useful current here. What if I want to bump it up to 140? Okay, it went up. It was about here, it went up to here. So it is delivering about 140 milliamps, although the voltage seems to have dropped. Yeah, it's down to 5 volts. So it may be getting a little too high for that current range. Turn the load off again, watch the meter. Yeah, it's not delivering the full rated current, although it is putting something out. So I definitely need to go through the setup on this and see what part of it isn't working properly. Checking these caps, feeling if they're even a little bit warm. Alright, well, enough testing on this for the moment. Turn the power supply off. Okay, it's time to address these capacitors, and for this large 3300 microfarad one, I've got this one. It has the same exact ratings, nice Nichicon part, but of course using modern technology it's way smaller, but it has the same capacitance and voltage. And this guy here has a 100 microfarad at 250 volts in it, and I've got this one to replace that part. And then it has two 40, I think they're 40 microfarads. One's at 250 volts and the other one is at about 200 volts. So I've just gone ahead and gotten two 47 mics at 250 volts each. No point in getting one at 200 volts. They can both be 250. So those three together will replace this smaller capacitor. Now, it's kind of a rat's nest in there. It's not awful, but to make it a little easier, once I pull those original caps out, I've got some perf board here, some vector board, that I'm going to cut out so that it mounts into the original screw holes, and then the the capacitors can be mounted on that. And I'm going to find some way to disrupt these capacitor junctions as much or as little as possible. Not quite sure how I'm going to do that yet. Sometimes it's only 2 or 3 things that have to be disconnected, but I'm reluctant to heat up some of these old parts because you have to put a fair amount of heat on it to desolder them. There's a lot of wiggling around that could damage the parts. So I'm going to see about perhaps keeping the old connections and then branching from those to the new ones. Again, I haven't figured it out yet. And for the neon for the front panel, I've got a replenishment of my parts drawer. I've got 10 neon bulbs of the C2A type. That's a extremely common neon bulb, and I'm sure that's what's in there. So I have that, and meanwhile I've been busy on eBay, and this unit takes 2 PNP power transistors, 2N2869s, and somehow I ordered this one by accident. But it came in, and then I ordered this pair of them that also came in. These are all apparently new old stock. That was what the sellers claimed. And then for the 2 transistors that go here, these are the smaller power transistors that are used for the overload and current regulation parts of the circuit. And there was a seller selling a set of 3, also new old stock. Oops, and I drop them all over the place. That was good. But they should be ready to go in there if I need them. They weren't that expensive, and I decided once I got into this I didn't want to have to find, oh, there's another part that's bad. I'm going to have to wait another, 5 days or whatever for another order to come in. So I just took the chance that I might need them. And if it turns out I don't need them, maybe I'll turn around and sell them on eBay. It's kind of interesting. I was making a wiring diagram of exactly how this small rat's nest, and also this one over here, but this isn't one. I've already recapped this area. And a couple of things didn't jibe with the schematic, and I came to realize that this capacitor here and this lead here is one from the old capacitor, and here's where I spliced on the new one. It was going to this terminal, and it should have been going to this terminal. It looked like it was always that way. So it was apparently always miswired. And I don't even want to hazard a guess as to what effect that had on the operation of this unit, although apparently it was in use at 2 or 3 different companies and or institutions, being that way, so apparently it couldn't have been too horrible, or maybe it was always considered to be sort of a marginal power supply. No idea. But anyway, because I really don't want to risk damaging these components from all the extra heat from desoldering them and reheating them, I've decided that I'm just going to use the cutoff wheel on my Dremel to saw away at the capacitor lugs. It's going to be a little harder with this. I might do this just with wire snips. These are thinner sheet metal. And keep the wiring going to those so they don't have to go through the desoldering process. And then I will mount the new capacitors on phenolic perf board from the other side, and I'll try to orient it so their appropriate leads come up in the correct locations, so they can easily just be tacked onto those. I think that's probably the sanest, if not the prettiest, way of doing it. Otherwise I'd have to come up with some surrogate terminals to solder everything to, and nothing's going to line up like the old ones did exactly. I could probably come up with something using this type of device, this kind of terminal, but again, then I'd have to desolder all this stuff, and I'm mostly worried about damaging components. So I'm going to try it the way that does not involve any desoldering. If that turns into a total abortion, then I'll probably just bite the bullet and desolder them and hope for the best. Okay, the two caps are out of there. These I cut through with the Dremel cutoff wheel, and these I went after with my heavy-duty wire cutters and just cut through them below the solder joints. So now I have to come up with the piece of perf board that's going to be going on here, mark its holes, and then figure out where the caps need to be to line up with their various terminals here. And that's what that looks like from the other side. Okay, I've made a piece of perf board that fits in there and has holes for all the original capacitor mounting holes and cutouts to dodge a couple of other things. So that's bolted in there now. I plan to anchor the caps with just a little blob of hot melt glue. On the big one it'll be around the rim. On the other ones, well, probably on the rim. I don't want them right next to the leads if I can avoid it. These two are 47 mics. This is 100 mic. Same lead spacing. I don't want to get them mixed up. I've got the board marked for the 100 in that position. And I tried to get it so the 3 minus leads are all within bridgeable distance of each other, and also so that the positive leads would come up right next to the tabs of the old capacitors so they could be tacked on there pretty easily. In the case of this cap, the distances are so great that while I have the original two terminals like this, the new cap terminals are going to go like this, and I'm going to have to put a little diagonal piece of wire from these over to the old cap terminals. And there they are, glued into place. Certainly less imposing than the original capacitors. And just for posterity, before I trash can these guys, 100 microfarad at 250, 40 at 250, 40 at 200. I'm replacing it with 100 at 250 and a 47 at 250 and another 47 at 250. This guy here, which the markings were covered up by the mounting clamp, but it does say 3000 microfarads at 75 volts, which I hope is what the schematic says. Well, the schematic doesn't say. That's a failure of Heathkit. They tend to leave out some interesting information on a lot of their yeah, there we go, 75 volts. You know, you'd think that they would put the capacitance and voltage as those are the primary characteristics on the schematic, but they tended to not do that. And the one I got to replace it is a 100 volt part, so it's more than adequate. As for these cans all being really close together, they are insulated, but never mind. The outer can is the negative lead, or electrically common with the negative lead, and on the original those are all the same, and they're all going to be tied together anyway, so even if they weren't insulated, it wouldn't make any difference. Alright, well, the new capacitors are soldered in. It's kind of hard to show it here, but I just took some 4004 diodes to get the thicker leads. My bus bar that I stock is a smaller diameter, and soldered it onto the capacitor tabs, and then just bent them up to solder onto the sides of the old capacitors' solder tabs. And did similar types of things for this capacitor. I took the 3 capacitors' negative leads and put them together into sort of a V-shaped bus and connected the circuit common wire that used to go to the case although it didn't go to ground. It was isolated from chassis, but it went to the can of the capacitor, and that's tacked on there. And then I had arranged the plus leads of the capacitors to line up with the tabs of the old capacitor, so the leads just went immediately to where they needed to be, and I just tacked them onto the old solder joints. So now I have to replace that neon that was broken. So there's the old neon bulb with one lead broken off, and the new CA2 neon bulb on the left. And I just need to stick it in this holder and wire it up to this switch, which is where it's getting its power from, off of a wafer on this switch here. Okay, that's taken care of. Okay, the power supply is on. I'm just doing a quick check of functionality here. I've got it on the 0 to 5 volt range, and the meter is on 10 volts. Notice that the lamps switch now with the meter. So the meter is saying I've got about 10 volts there, and I can vary it between the 5 and 10 volts approximately, which is what this switch says. And I've got my electronic load up here, and it's reflecting the change in voltage. The meter seems to be fairly on, and I can switch over to current, and it should be 50 milliamps maximum, so that's maximum. It's reporting about 23 milliamps. Well, this says it's doing about 19 milliamps, and I can crank the current all the way up to 50 milliamps. It's a little bit off, but it's in the ballpark. And now I can crank my load down to, say, 10 milliamps, and that's off. It definitely is not super accurate. Now if I want to go up in voltage, I can go to the 0 to 15 volt range. So now I'm not getting any meaningful change from the pot there. Although, interestingly enough, this says that I'm going from 10 to 15 volts. Oh, it's in current, duh. So, from 10 to 15 volts. Got it at 15 volts. And I still have it limited to 15 milliamps. This is saying that I've got it set to about 7 amps. Let's see here. I want to go to 10 milliamps, and it's kind of in the ballpark. If I go to current here, it's reading approximately 10 milliamps. And then once again I can crank this. It's still reading all the way up to 50 milliamps. I can actually go a little higher. I don't want to peg the meter, but the meter is saying 50, and it's about 46 according to this, and it's delivering the 15 volts. I can turn my knob here, go back to voltage mode, turn my knob down to 10 volts, and it reflects approximately that. It's still delivering the current that I wanted it to. I'm going to set it to something like 40 milliamps. Back to voltage. So it's doing about 40 milliamps. The voltage does seem to have sagged. Let me see here. I should be able to go up to 15 volts here, but I'm not able to. If I go back to 5 to 10, yeah, it's not happy with me now. It was working better, but now it's starting to not kick out like it should. So I need to go through some troubleshooting here. Let's just see if anything is getting warm. These two guys are good. Nothing seems to be warm back here. I'm not sure if I have a switch problem or if I have something that's heating up problem. This resistor gets stinking hot, too hot to touch, and I don't think it should get that hot. So there may be a problem in that circuit. I'm going to power down and see if anything else is getting really hot. Well, this resistor here, this 1200 ohm resistor, 1.2K, was getting warm but not hot. This guy is just radiating heat here. I can't even touch it. This resistor across the big cap was fine. Essentially no warmth on that at all. All the diodes seem to be about right. This one maybe feels slightly warm, but that may just be due to its proximity to this guy. Nothing over here seems to be hot. So that was a problem before I changed the caps out too. There may be some sort of a problem in this. This is the main power supply, this is the bridge rectifier, this is the main filter cap, and then everything else around here is part of the Zener voltage source that is used as a reference, to provide a reference voltage for the regulator circuit. And there may be something going on there. If this resistor gets too hot, you know, whatever else is going on there that's making it draw that much current. I don't think it's designed to get that hot. Alright, I found that this transistor wasn't working properly on a diode tester, or on a transistor tester. It was showing up as a couple of diodes instead of as a PNP germanium transistor as this one did. So I took one of my replacement ones, which also tested correctly, and put it in the circuit. And then I was testing the two power transistors on the back, and one of them was clearly the original because it had the Heathkit model number on it. It tested correctly. The other one tested as a couple of diodes. I know transistors can often test as a couple of diodes, but I thought it was odd that it didn't test the same as the other one, although this one had been replaced with a non-Heathkit part at some point in its life. So I took a chance and replaced it with one of my eBay purchased new old stock transistors. So now I have the power supply set up to deliver 12 volts. It's on the 10 to 15 volt range. It's set to 12 volts. And from this point on, I'm going to switch it back to current mode and watch its current meter. I can see that I've got 12 volts up here on the power supply and that the load is on. I've told it to pull approximately 100 milliamps out, which it says it's doing, and it's reading about 100 milliamps here. Now if I crank the current up to 200 milliamps, approximately, it says it's delivering that, and it's reading 200 milliamps. I'll crank it up to 300 milliamps. Says it's putting it out. It's showing that pretty precisely here. Go up to 400 milliamps. says it's putting it out, and it's reading it. So that's an improvement. It wasn't doing that before. Now I'm going to kick it back down to a couple hundred milliamps. It says it's putting it out. I want to go for a higher voltage. I'll switch this back to voltage. I'm going to go up to the 20 to 25 volt range and adjust it for, it should be on this scale, I think. You can go from 20 to 25, and I've got it set for about 24. I'll set it with this. 24 volts. It's about what it's reading here. Go to current mode. It's putting out 200 milliamps, which is what it says it's doing here. Go to 400 milliamps. It's putting it out. It's reflecting it here. I'm going to go to the 35 volt to 40 volt range, which if I go to this, I can go in that range. So I'm going to go right up to about 48, or what is it here, 38 volts. I'm going to put it right up at 40 volts. Doesn't quite get there, but well, let's put it to 36 volts. And it's reflecting about 36 volts on the meter. It's still putting out 400 milliamps as I've told it to. The meter still reflects 400 milliamps. I can take it down to 200 milliamps. It says it's doing it. The meter says 200 milliamps. Back to voltage. I'm going to go up to 50 volts. And I want to set it for about 46 volts, which is about there. And it says 46 volts here. And I'm calling for 200 milliamps. It's delivering 200 milliamps. And the meter says 200 milliamps. I'm going to take it down to 100 milliamps pretty accurately. It's reflecting 100 milliamps pretty accurately. It is putting it out. This is doing everything I want it to do. I'm slowly stepping down in my voltage. I'm going to go back down to the 10 to 15 volt range. Put it in voltage mode. Adjust for 12 volts. And it says 12 volts pretty accurately there. And it is putting out the 100 milliamps that's requested of it, and reflecting 100 milliamps on the meter. I would say this power supply is completely functional at this point. Doesn't even look like I need to recalibrate it. It was acting a little squirrely before, but with those two transistor changes, its meter is well within the accuracy I expect from it. I'll turn the power supply off, take my load off, turn it off there, tip this guy up on its side. That resistor is still really hot, but it's working. Since I don't have any actual use for this power supply other than nostalgia, but since it is clearly working, and during my tests here, not all of which I've shown on the video, I've had it on for about half an hour running higher voltages and you know, pretty close to the top current rating on each limit. And it's continued to put out. It's been very accurate, so I'm not really going to ring this thing out anymore. I'm going to count my lucky stars that it seems to be working at this point without further screwing around. And gonna reassemble this case. Okay, these old chassis screws are kind of corroded. They're nickel plated, and from Bolt Depot I bought some nearly identical ones that I believe are stainless steel. What are they made of? Does it say? Yeah, they're stainless steel truss head screws, truss head machine screws with the Phillips, just like the originals. I should have used these shorter ones that I bought, but I used a few of those for something else on here that looked cruddy, so I'm going to use the slightly longer ones for this. It'll look a lot better cosmetically. And I want to store my supply of spare transistors that I ordered online, and I really screwed this up. I had meant to only get 2 of the powered pass transistors. One of the transistors that's used over here, that's the one that's used for current overload or current limiting. It's also a pass transistor, but it's one that normally is set up with a very low resistance and then increases its resistance if I get close to the the maximum current I've dialed in. So there's one of those here, and then I've got 2 more of these lower power but still heat sinked germanium transistors that are used for the current limiting and pre-regulator stages. And I don't see the point of trying to turn around and resell them. So I think this is robust enough mechanically. I can probably kind of jam them in here like this. I think the case will go on. It'll just hold it there between the case and this big cap. It won't rattle around. Nothing over there gets hot, so you know, it's by the meter movement and so on. It should be fine. Alright, the case bottom is on. The 4 rubber feet, the 3M bump-on types, which are our original type that Heathkit always used, except as I said earlier in the video, this should have had the beige or tan ones. Those are practically unobtainium anymore, even though 3M still makes them, unless you want to buy large quantities. Only the black ones seem to be readily available in smaller quantities. So the black ones it is. And there's the top cover put on. I think the paint color I got here, which again was the one I eventually used, was the Rust-Oleum Camouflage khaki 1917 color code. Looks good on here. It's perhaps not exactly what the original was, although it's very close. And I think it looks good with the shading of the original paint on the front panel. I'm not sure if the original was that lighter color. I don't think it was. I want to say it contrasted a little bit, but again, not sure. The front panel cleaned up nicely. Looks good. The back side isn't quite as nice. It has a few blemishes. I was able to mostly restore the Heathkit label to legibility. At least it lays flat. But there were quite a few dings and gouges and places where I patched, and the colors don't completely match. So that's sort of the ugly side. Okay, quick overview of the power supply. the IP-27. Starting on the left, we have a meter which is graduated from 0 to 15 and from 0 to 50. Depending on the various ranges and whether we're looking at voltage or current, we'll look at one scale or the other. Everything on the panel is color-coded with red or black to tell you which scale is appropriate. The meter can read voltage or current depending on this switch down here. Current on the left, voltage on the right. And there are these two neon bulbs that indicate current and voltage. So if you're monitoring current, this will light up. If you're monitoring voltage, this one will light up. And those neons are above the control stack for that characteristic. So if we're monitoring current, this lights up, and here are the two controls for setting current. If you're monitoring voltage, this lights up, and you can see the two controls for setting voltage here. Both the current and the voltage have coarse and fine adjustments. The coarse is with multi-position selector switches. The fine is with potentiometers. For the current, we can select 50 milliamps maximum, 150 milliamps, and Heath, like many other companies in those days, was not so careful about appropriate abbreviations. Current convention anyway, or today's convention, more recent convention, is that any unit of measurement that's based on somebody's name should be capitalized. So amp is after ampere, and or amp or ampere is named after a guy, let's put it that way. And therefore A should be capitalized. And our convention these days, and I think it's always been true, but it's often overlooked or done incorrectly, is that units of, or not units of measurement per se, but the system they're in. For example, if it's in the metric system, should follow the conventions of that. So a capital M means mega, and a lowercase m means milli, and so this should be small m, capital A for 50 milliamps. And Heath wasn't the only offender in that regard. But you can get 150 milliamps, 500 milliamps, or 1.5 amp maximum, and then the fine control, if it's fully clockwise, is that highest number, and if it's in the middle, it's roughly half of that, and so on, down to zero essentially, or very close to it. So normally you'd probably just have this turn fully clockwise, and then you'd select an appropriate current range. If you're not concerned at all, you might just leave it up here, and the power supply will put out as much current as it's capable of. But if you have some sensitive equipment that you don't want to put too much current through, you might decide, well, I never want the current to go above 150 milliamps, for example. So you'd have the switches and knobs set for that. And then the voltage, the most clockwise position of the voltage switch is the power switch for the whole power supply, which is kind of unfortunate because you have to cycle through the whole switch every time you want to go from off to whatever range you want, which can add to a lot of wear and tear on the switch. On the other hand, it may help keep the contacts wiped and free of corrosion, so there may be a plus in that. Anyway, it's off, and then you can adjust the voltage in the 0.5 to 5 volt range, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30, 30 to 35, 35 to 40, 40 to 45, and finally 45 to 50. And then within that range, for example 10 to 15, when the fine control is fully clockwise, counterclockwise, it'll be the lower number, in this case 10 or thereabouts. And when it's at the full clockwise position, it'll be the highest number. So for example, if I've got 10 to 15 volts set here, the meter will only move between here and here, although as I mentioned a minute ago, the lower end is not as calibrated as the upper end. So even though it's supposed to be 10 milliamps, probably at full counterclockwise, it'll be somewhere below 10 milliamps, but it'll certainly encompass the range, or 10 volts. It'll certainly encompass the range 10 to 15 volts, and full clockwise should be calibrated to give you the full scale that matches this. This is the main output on and off. So the power supply could be set up and put in standby mode with the switch down here, even though the supply is on and set up, and then throwing the switch here turns it on. Now, one thing I thought was curious about this was that I assumed that you'd be able to set the voltage up with this in the reset or standby position and then apply that voltage. But on this supply, the meter doesn't read anything, and neither does the output reflect anything unless this is actually on. So anyway, that's what that does. And turning it off here, it says it resets it. I'm not sure what it resets. The operating instructions don't really seem to go into that in any great detail. Down here we have our 3 binding posts, which if backed out far enough can either accept a fork lug, or you can stick a wire through the hole and then tighten down on it. Or you can put a alligator clip in the end, or you can stick a banana plug on a cable into here. There's the positive and the negative supply. These are isolated from ground. And then the middle one, which really should be green, but on here it's black, is connected to chassis ground and to earth ground through the power cord. So you can actually jumper these two together, for example, if you want the negative side of the supply to be grounded, or you could have the positive side grounded. The power supply also allows for parallel operation, as really does almost any regulated power supply. You can have multiples of them wired in parallel if you need more current, or you can wire them in series if you need more voltage. Each individual supply only sees its own current and its own voltage, so it's not really like that much of a design feature. It's just something that most power supplies can do. Of course, if you're going to wire power supplies in parallel, they need either diode isolation or resistor isolation from each other, so that they don't fight each other over small differences in their voltage settings. In other words, one power supply isn't trying to regulate all the other supplies that are wired in parallel with it. It only regulates itself. The back side of the supply has several adjustments. The DC regulation, which is something you can stick a Phillips screwdriver into and tweak a pot that feels like a wire wound pot from the sound it makes when you're adjusting it, and it very well may be. And these other 2 trim pots are also the same way. On the inside, they're not really trim pots, they're panel potentiometers that just don't have shafts sticking out of them. They're fairly large. So for voltage calibration, you would go to the highest voltage range and adjust this for a true 50 volt output, and then everything else is supposed to scale from there, assuming that your internal component values have reasonable tolerances. When optimizing the Zener reference voltage power supply, it's best to have a particular current going through the last Zener in the reference circuit, and the manual says you should set it for 4 milliamps. The silk screen here says you should set it for 5 milliamps. So there's some inconsistency there. The manual also says this is not critical and it shouldn't have a wide span, so presumably you could have it set almost anywhere and it's not a big deal, but I'm just leaving it where it was. I cycled all of these during the course of the restoration. I cranked them back and forth a few times to make sure they were making good contact and that they weren't just sitting on a ball of oxide or something. And the DC regulation is to fine-tune how the regulator itself works. It's not to calibrate the voltage. And those are subtleties of the circuit. And then finally, if you're going to use the front panel meter to set the Zener current, you have to move this switch to the Zener current mode, at which point it reads 0 to 5 milliamps, and then you would adjust this one for whatever it says in the manual or here, which would be 4 if it's the manual or 5 milliamps if it's according to this, but again it says it's not really all that critical. Otherwise you'd leave the switch down and then the meter displays either current or voltage according to the front panel switch. This is a cap, an insulating cap for the series pass transistor that's used to reduce power supply voltage if the current being supplied has reached the maximum current setting. That's the only way you can reduce the current, is by increasing the resistance in the power supply circuit so it delivers less current to the load, and it does that by delivering less voltage to the load. So that's what's behind here. It's a different type of transistor from the other two, and this matched pair of transistors under these two caps and on a bigger piece of aluminum for better heat sinking. These are the two series pass transistors for the voltage regulation part of the power supply, and those will be covered in the theory of operation and schematic overview part of this video later on. And then finally there's these two horns here, or hooks, which allows wrapping up the power cord in the back. And around the sides we have these two trendy at the time but really pretty awful carrying handles that are on steel straps. They can be pulled out. It's kind of spring steel, and get a grip on it, which means your knuckles are banging in to the sharp sheet metal here. And the springiness inside the plastic sleeve is just a strip of spring steel, kind of like a very thin leaf spring, and it wants to snap back in place. Even back in the 70s when this series was being phased out and they went to more rational and ergonomic case designs for Heathkit test equipment, even then I saw these things and thought they were wretched. They look kind of cool, but they're really a pretty bad design. And yet, that's what Heath had. The other side's identical. So that's an overview of the physical power supply. Okay, an overview of the schematic, just to wrap this up. We start out with a transformer whose primary has two coils, and it can be connected either with the coils in parallel or in series, depending on whether it's going to run at 120 volts AC or 240 volts AC, which is the alternate connection. There are three secondaries, this one, and this one. This one's got multiple taps. Let's start out with this one here. This is the reference voltage power supply. Any voltage regulator used in a power supply needs to have some sort of a reference. It may be as simple as a Zener diode, it may be much more elaborate. This one starts out with a fairly high voltage. It's trying to obtain about 50 volts with a fair amount of precision and stability. So it starts out with a half wave rectifier off of a 170 volt AC secondary coil that's filtered with a 100 microfarad capacitor, and then through this resistor and this 110 volt Zener it produces a roughly 110 volt DC voltage at this point, and then that's filtered a bit more with this resistor and this capacitor, and then it's applied to this 68 volt Zener here, which knocks it down to, again, about 68 volts. The voltage could be down to 65 volts, and it depends where that is measured from. That's why these voltages are a little different than the Zener voltage. And then that is applied to a third Zener diode, which is also back to the negative of this supply, and that is a 56 volt Zener, so it's knocking it down to 56 volts across the Zener. And then there's also these two resistors here between the anode of this Zener and the negative of the reference supply, and that is used to as a current shunt, essentially, to tap off with the meter via these two wires A and B, which are essentially across this shunt resistor that goes to the meter circuit. And that's because this Zener's voltage is most stable at a particular current going through the Zener, and this potentiometer here is used to adjust this higher voltage, and it's stabilized with this capacitor, and that's adjusted to get the ideal current through this Zener and thereby give the most stable and accurate Zener voltage. And then that voltage is applied through this calibration fine-tuning resistor to this big bank of resistors on the coarse voltage selection knob, and then through the fine voltage adjustment potentiometer through the coil of the relay and up to the base of the error detector transistor. The other side of that circuit is connected to this bus, which is the positive output of the power supply. So this is essentially comparing the reference voltage after it's been conditioned by these resistors, both the fixed ones on the selector switch and the trim potentiometer, or not the trim potentiometer, but the fine voltage adjust potentiometer. So you essentially get a reference voltage knocked down by whichever range you're in, and that's applied to this transistor, and it's comparing it against the actual voltage coming out of the power supply on the plus lead. And its sensitivity is dampened somewhat by this RC network here that keeps it from being overly sensitive to differences between the reference voltage and the actual output voltage. But what this is going to do is change its collector current depending on the difference between the reference and the actual. And then that's fed into the amplifier, which is the same kind of transistor. And these two transistors are, by the way, the ones that in the earlier video look like aluminum standoffs with a male threaded protrusion on the top. So that's what those guys are. Anyway, that error signal that's saying, you know, there's a certain amount of error between the reference and the actual is then applied through the error amplifier, and then that drives the two series pass transistors, and these are the two big ones on the heat sink on the back. They're essentially wired in parallel, but each one of them has a 0.33 ohm resistor on its emitter before they're actually tied together, and that allows them to be balanced, and there can be small differences between them that are made up by the resistors here. The bases are biased also from this reference voltage supply through a thermistor and a fixed resistor, and that allows another input to be brought into this. Not only are these transistors adjusting their conductivity according to the detected error that's been amplified, but also according to the temperature. Anyway, so there is a thermal compensation for this circuit because of the thermistor. And what you've essentially got here, and it's outlined in these heavy lines, going through here and here. Let's go to the main power supply now that we've talked about this part of the circuit. One of the big problems with especially linear pass transistor type of power supplies, regulated supplies I should say, is that you generate a lot of heat when you start out with a high voltage input to the regulator, and then you're taking out just a small voltage. That means a lot of voltage has to be dropped across the pass transistor elements, which are here. To minimize that, the way Heath did this is you have to divide the output into small voltage ranges, and different taps of the secondary winding are taken off to get different voltages, and thereby start fairly close to what you want the regulated voltage to be. There's a full wave bridge rectifier and a single filter capacitor with a bleeder resistor that'll discharge this as soon as the power supply is turned off, so you don't end up with a big charge being stored in this capacitor. So you have various voltages from just a few volts to over 50 volts on this capacitor, depending on the voltage course range switch. And the positive side of that goes through the relay contacts, that's the overload relay contacts, and then through this fine current adjust potentiometer and the coarse current switch, which has a series of resistors on it. Those end up in a series parallel arrangement with these resistors. And essentially what you're doing is these are acting like a current shunt. So current is being sensed by the amount of current going through here, and then it goes through this current limiter transistor, which is normally turned full on, and then it goes through another current shunt, which is also part of the coarse current control switch, and then through another current shunt, and then finally through the reset standby switch on the front panel, and then out the positive terminal. Returning current from the load comes in the minus terminal, and it's immediately presented to the two series pass transistors. And then half the current goes through one of them, half the current takes the other branch and goes to the other one. They merge at the collectors, and they just come straight back to the source power supply. So the voltage here is being compared to the reference voltage from the Zener by this circuit, and then applied to control these in whichever way is necessary to get the right amount of conductivity through them so that they adjust the output voltage until there is no error. And that's a normal series pass voltage regulator type circuit. Some sort of pass transistor, it could be in the negative lead, it could be in the positive lead, it doesn't really matter. And then some sort of a reference that drives them. So this is all pretty typical here. Now over here we have this additional low voltage secondary coil. It's only 7 volts. It's half wave rectified and filtered with this 250 microfarad cap, and then it's applied to this diode here and through the Fine Current Adjust Potentiometer, which, remember, is part of this resistor network comprised of the pot, this resistor, and these resistors. And the way this transistor is wired, as I mentioned just previously, it's set up to normally be in full conductivity, so it has essentially no resistance from its emitter to its collector, and it presents no restriction on current flow. But if the amount of current flowing through this leg of the power supply gets to be above a certain amount, again, according to the voltage dropped by these resistors, whichever one is selected according to the range, and by the fine current adjust, it starts raising the voltage at the wiper of this potentiometer. And when that voltage, along with the forward voltage drop of this diode, exceeds the point where the diode is forward biased and starts to conduct, then it starts presenting an input here that turns off, progressively turns off this transistor, making it have more and more resistance from its emitter to its collector. So in other words, as the current gets to be excessive according to this selection here, it starts feeding into this transistor and making it increase its resistance, thereby decreasing the voltage in the circuit, so it will not exceed the current that's been set by the user. This is also a series pass transistor, but it's being used to restrict the voltage in such a way that you don't exceed the set current. And remember, Ohm's law says that you're going to have a direct linear relationship between the current and the voltage. Now this circuit here is also part of the course current adjust, and this is a current shunt. Notice these are all real low values, like 2 ohms, 0.7 ohms, 0.2 ohms, 0.1 ohm, and the current flowing through the circuit drops a small amount of voltage across whichever these resistor or resistors are engaged by the switch, and you end up with a small amount of current flowing from F to E, and that is applied through the two switches here, the one on the rear panel, normal and Zener current, and the one on the front panel under the meter, which is the current voltage switch. And it essentially puts that current through this 1 milliamp meter, and you can detect what the current is ratiometrically. Now if the switch down here is selected to the voltage position, then it's using these switches down here. Let's see, which one is it? Yeah, it's these two switches here, which provide yet another shunt. It's part of the actual voltage from the positive terminal through the meter circuit up here and back to negative. And by doing that, it's able to monitor the voltage of the power supply output through the 1 milliampere meter. Now if this other switch on the rear panel is switched from normal to Zener current mode, now the meter is taken out of the normal power supply's current or voltage sensing, and instead it's placed across this resistor down here, which remember is sensing the Zener current in the Zener reference subcircuit. And that's used for setting up the power supply in the first place when you want to optimize your Zener current. So that's why that switch is on the back. During setup, you put it in Zener current mode and adjust the Zener current potentiometer here to the prescribed amount, and then put the switch back into normal, after which the meter follows the current and voltage selector on the front panel. And there's also an extra gang on the current voltage switch, which applies AC power to one or the other of the two neon bulbs, indicating whether the meter is showing current or voltage at the given moment. Now there's one or two other little things here which I'm not going to dwell on, but this circuit here with this capacitor and this relay coil, this is still in the path of current being used to control the error amplifier, and it's connected in such a way that it's used as an overload sensor. If the current flowing into there is greater than a certain amount, which only happens if you're really overloading the supply and it's really having to kick a lot of current through here to get the power supply to conduct enough to keep up with the load, then eventually you'll get to the point where there's enough current going through this relay coil and its shunt resistor that the relay coil will energize and transfer the relay contact switches here, which breaks the connection from the source power or the power source to the output of the power supply. So it's essentially like turning off the power to this whole loop temporarily. Now, if you didn't put any damping on that, as soon as it breaks it, then of course the current is going to go down, the overload will disappear, the relay will immediately re-engage, and the whole thing will chatter, which is bad for the power supply and even worse probably for the load. So there's this capacitance element here, which is effectively across the relay coil circuit in such a way that once the relay coil has been energized, this capacitor has to charge or discharge until the relay is allowed to de-energize. And that causes, whenever that relay is energized and it breaks the circuit, it can't immediately re-energize. It takes a brief period of time. I don't know exactly what that time is, but when I was testing it, it seemed like it was a couple of seconds. So it's just slowing down the automatic reset of the overload circuit. So let me see if there's anything else I missed on this. We got the current limiting, we got the main power supply, the reference, the shunts, the overload, the error amplifier, the pass transistors, and the metering circuit. I think that was it.